Sometimes you have a need to generate a single pulse with a well-defined duration. There are quite a few reasons that you might want to do this, and we will probably see some of these in some of our other videos. However, the 555 timer is a real champ at generating such single well-defined pulses. As mentioned in the overview video, there are three primary modes: monostable, astable, and bistable. The astable mode is used for oscillators. To generate single pulses, we use what is called the monostable mode. If we look at a block diagram for the 555 connected as a pulse generator, as a monostable, the standard circuit has a resistor and capacitor connected to pin 2, which is the trigger input. That's where we will initiate the pulse. And it has another resistor-capacitor pair, which is used for setting the width of the pulse out. Also note we've got our standard 0.01 microfarad capacitor connected to the control input, pin 5, which is there to help stabilize that 2/3 VCC point in the 5K voltage divider, if you recall that. We'll see that in a moment. Also note that I have not shown the two power supply bypass capacitors. It's fairly common to leave these off of a circuit diagram just so that you don't clutter the diagram up too much. But remember, to make sure that the device operates reliably, you really need to add a 0.1 microfarad ceramic and a 1 microfarad electrolytic between the power supply and ground. It's difficult to talk about how this circuit operates when you just show the 555 as a box like this, so we're going to show the same circuit expanded with the 555 shown as a block diagram. We're going to start by assuming the output is low. Now, a couple of things that we need to talk about while this is low. First of all, note that if it's low, we do not want that lower comparator to be turned on, which means that the trigger input, the inverting input to that comparator, needs to be at a voltage higher than 1/3 of your power supply voltage. Thus, R sub T. R sub T holds that trigger input, pin 2, high. We'll talk about the capacitor C sub T in a few moments. Also note that if the output is low, that point between the flip-flop and the output buffer is inverted, and so the base of that discharge transistor is high, the discharge transistor is on, and so the capacitor C is effectively grounded through the discharge transistor. So the voltage on C is very close to 0. Any current coming through the resistor R that would normally charge C is diverted through the discharge transistor to ground, so it does not charge the capacitor C. Alright, that's our starting point. Let's consider what happens if we put an input on the terminal labeled input down there at the bottom connected to C sub T. First of all, if the input is just a constant, then C sub T will charge to whatever value is necessary in order to maintain V sub CC on pin 2, thus keeping that lower comparator off, as we assumed with the output low. If the input changes slowly being defined by the values of R sub T and C sub T, then the capacitor can charge or discharge as necessary to fairly closely follow the input voltage and maintain a voltage very close to VCC or a high voltage on pin 2, thus also keeping the comparator off. However, if the input changes very rapidly, then the voltage at the other side of the capacitor has to change by essentially the same amount. Since the voltage across the capacitor itself can't change instantly, then the trigger input connected to the other end of the capacitor will change by essentially the same amount. If the input went positive very rapidly, then the trigger input would just go higher, keeping the comparator off. However, if the input dropped suddenly by more than 2/3 VCC, then that would drop the trigger input below 1/3 VCC, the comparator would turn on, the flip-flop would set, the output would go high, but now again, remember that inversion there. Since the flip-flop is high, the base of the discharge transistor goes low, the discharge transistor turns off, and now the current coming through R from your power supply is no longer diverted to ground and begins to charge C. Now at the same time this happens, C sub t, that input capacitor, starts charging via R sub t, and so the trigger input rapidly goes back to VCC, which of course turns that lower comparator off again, but the flip-flop is now set. It's not going to change until either the reset pin goes low, which it can't because we tied it high, or that upper comparator turns on. Now, in order for the upper comparator to turn on, the voltage across C has to reach 2/3 VCC. So, as we saw a moment ago, the capacitor is now charging through R. It's charging up toward VCC. Eventually, it will reach 2/3 VCC. When it does so, the upper comparator turns on, it resets the flip-flop, the output goes low, the inversion in between the flip-flop and the output buffer goes high, the discharge transistor turns on, it rapidly discharges the capacitor C, and the current through R, which would normally charge C, is again being diverted to ground through the discharge transistor. And at this point, we're back to where we started, with the output low and the timing capacitor fully discharged. Now, one thing to note here is that if you were to get another rapid drop on the input of more than 2/3 VCC while the output was still high, nothing's going to happen, because if that did happen, it would set the flip-flop, but the flip-flop's already set, so nothing changes. So you can't re-trigger the pulse and sort of restart the timing of the pulse while the pulse is high. Any incoming large negative edges on the input while the output pulse is still high will not affect anything. Now, as far as the output pulse width, that can be calculated as 1.1 times RC. Now, we're not going to derive that here. We may do that in a future video. That's a standard result and is not too difficult to derive. Also note that the rapidity with which the trigger input returns to VCC after receiving a negative edge on the input depends on R sub t, C sub t. You need to select R sub t and C sub t so that the voltage on the trigger input goes high fairly rapidly, at least relative to the output pulse width. By the way, the minimum pulse width that you can reliably achieve with a 555 timer is about 1 microsecond. So if you need pulses narrower than about 1 microsecond, then you need to go to a different device. But for many applications, the 555 works like a charm. In future videos, we may look at some more complicated versions of a monostable circuit for special purposes. But for now, we'll move on.